Hello folks, welcome to Rational Science, and today we're going to be talking about the neutrino, or as the Italians I guess would call them, a piccolino neutron. In fact, it was named by the Italians. And before we can get a handle on the neutrino, we need to get some foundations. And there's at least two of them I want you to be aware of today. One of them is the notion of the word field. What is a field? And the other one is one we talked about last week, which is mass. Okay, what is mass? Or better said, what the hell is mass? That's a better way of putting it. Okay, so let's start with this. This was the original planetary atom of the first couple decades of the 20th century. Okay, and that's been modified quite a bit. Here's the, you could say, the modern version. Okay, I'll put it here side by side. Okay. Now, I want you to understand that that picture on the right is a little misleading, okay? And by the end of today's lecture, you should be able to tell me why it's misleading, okay? Should be able to tell me why that picture of all those particles inside the nucleus is misleading, okay? That's essentially what the lecture today is about. Okay. Here we have all these particles that are allegedly inside the atom. They're subatomic particles, okay? And we start out with a standard proton and neutron. Everybody learns that in high school. But then it gets a little more complicated, okay? We have the up quark, down quark, charm, top, strange, bottom. We got all these things that they found out there. We have pions, muons, electrons, the taus. We have the gluons, the W bosons, the Z boson. And we should not forget, the mass particle, the particle of mass, the Higgs, the graviton, obviously, they're still looking for that one. Photons that are buzzing around, neutrino, which is the one we're going to talk about today. And then you have all these other particles or quasi-particles or semi-particles or whatever particles that they've invented for just about everything. We have the soliton, we have the phonon, the particle of sound. We have the tachyon, one that travels faster than light. We have the chronon, the particle of time. And so on. We've got all kinds of particles out there. And yeah, it makes you kind of wonder, right? And that's not enough. There's another issue. There's another level of complexity that you have to add to that. And here it is, the fact that you have antiparticles. For example, this is the hydrogen compared to the anti-hydrogen. One has an electron, which is negative. The other guy has a positron, which is positive. And the proton is the opposite of the antiproton, and so on. And you have antiparticles for every particle out there, okay? And you say, is this kind of crazy now? Are we going nuts here with so many particles? Let me tell you what the problem is. The problem is that quantum field theory, right, says that every particle is a vibrating field. That's what it really is. And that's also what string theory says, essentially. They say, look, there's this line that's vibrating, and that's your graviton. And for sure, they'll extend it to every particle in quantum, to the electron, to the proton, to the neutron. They'll extend and say, oh, what's the neutron? It's a vibrating line. So all of these are vibrating fields, lines, whatever you want to think about them, okay? So let me show you a little bit of what the problem I see, okay, with that. Okay, let's go with the first one here. First, we go with the background radiation, okay, cosmic background radiation, and you can say that this is the field of temperature. Okay, so we have a temperature field. Okay, let's make this a little more complex. Let's add the gravity field, because you have space-time, and space-time is made out of a field, right? It's what is space-time? Space-time is some kind of vibrating field as well. Okay, so we have to put the gravity field. Okay, which is whatever space-time is. Okay, but on that we have to superimpose now the electric field. Like if you have electricity in your house, well, that's not the same as gravity. Okay, so you have to add these fields one right on top of the other. Okay, they kind of superimpose. Okay, and we don't stop there. Obviously, here we have the magnetic field. Okay, you know what a magnetic field is. It's what keeps two magnets together, right? Okay, so now we add the magnetic field to these fields. We're going to superimpose all these fields, okay? And we don't stop there. We have the Higgs field, which we talked about the other day. Let's assume this is the Higgs field, okay? And so you can see it's getting quite complex there. Okay, add now the one we're going to talk about today, the neutrino field. Okay, let's assume this is the neutrino field. Okay, so we're going to add this one to the pile. And you can see what's happening here. All these fields are kind of superimposing. Okay, and of course we got to think about the electromagnetic field, and I mean light, because light is not exactly magnetism, and light is not exactly electricity. So even though one is the electric field, the other one is the magnetic field, the electromagnetic field, which underlies light, the waves of light, well, they're a little different than electricity and magnetism. So we have to keep those as separate fields. And then, of course, you've got, for example, here's the, I'm going to illustrate this as the pion field, because, you know, you have pions out there. Okay? And so you can see on the right how complicated this is getting. Here's the muon field, because pions decay into muons. Okay, so we're going to add that one in on the pile. And so the question is, you know, what do we have in the end? Well, we have a bunch of fields. And here, you know, assuming this is what a field looks like, a three-dimensional notion of a field, whatever that is, it's some kind of a fishnet. Okay, it's, I don't know, you can say it's a trampoline, it's a canvas, you know, they have all these synonyms for that, but what you're staring at essentially is some kind of fishnet. And the question is whether this fishnet is for real. Okay? Is it for real, or are we talking about what is this thing? And so we have one issue here, the first issue. And the first issue is that people always ask, for example, in the case of the rope model, how is it that all these ropes, why can't I see them? Why can't I touch them? How do they avoid tangling? It'd be nice if these people would go first to quantum mechanics, to quantum field theory, and ask them, well, you have all these fishnets out there, three-dimensional fishnets, or maybe four-dimensional fishnets. How do they avoid tangling? You know, I mean, here you have, and they're all different fields, by the way, okay? Keep that in mind. They're all different fields. You have the neutrino field, the muon field, the electric field, magnetic field. You have all these fields out there, and they're superimposing out there in space all around us. How do they avoid tangling? How can we distinguish one from the other? See, when they talk about fields, they usually talk about one of them at a time. They'll talk about the gravity field, or the gravitational field, or they'll talk about the electric field, for example. But they never talk about them all together, because then people might wonder, hey, how do all these fields, you know, avoid tangling? So that's the first question people should answer before they ask me to answer, how do the ropes avoid tangling? Okay, how's that for a deal? Okay, that's the first issue. We've got all these fields superimposed upon each other. One of those is going to be the neutrino field. Okay. How about mass? What do we have with mass? Well, I'm going to start with some of the comments that people made, because there were several comments on the issue of mass. People are concerned about, you know, what really is this mass thing? So they have questions about it. And I discussed that last week, came from that lecture, okay? Here's one fellow, he says, I thought mass was volume times density. Okay, seems straightforward. Yeah, it is, but if you look at the chart there, you'll see that density is equal to mass divided by volume, and volume is equal to mass divided by density. So what have we learned? Well, we learned that these are calculations. These are not definitions. We don't know what mass is. We don't know what density is. We don't know what volume is. What we know is how to calculate them based on these relations. Okay? So, yeah, people say, you know, what is mass? And they give you an equation, and they say that's the definition. No, that's not a definition. That's how to calculate density. Okay? For density, you can look it up in the dictionary and it'll give you a definition, okay, of what density is. And the question is whether you want to accept that definition, especially if it's just circular, if it's a tautology, like, you know, density relates to volume, volume relates to mass, mass relates to density, and all of them relate to each other. So all you have is a circular argument. All you have is a bunch of concepts. Okay? So this is the issue. You have to be careful about definitions. Definitions have to be independent of anything else, in the sense that you don't chase your tail around with definitions by putting synonyms or whatever. That's not a definition. And again, you know, to say mass is equal to volume density times density, all you're saying is how to calculate mass. Okay, so that's the first issue. That's not a definition of what mass is. We don't have a definition of mass today, as I discussed the other day. Okay, here's another issue that someone raised regarding mass, regarding the lecture I gave the other day. The photon is massless. Another theory is proposing that the mass equal to 0 is the result of plus m plus minus m, following the same idea of E equals E minus plus E plus. However, what does mean negative mass, negative kilogram? Good question. Yeah, all they're doing is doing accounting. putting pluses and minuses in front of an undefined concept called energy. And so, again, for calculation purposes, they can do all that stuff. What does it have to do with physics is the question. Because unless we see a physical object in there, we cannot give a physical interpretation to that equation. And that's where we stand today. Okay. So another fellow, says exactly or more or less the opposite, or he kind of came in around the same lines, actually. And he says the following. He says, when a photon carries an image of a star, does its mass increase? So it can't be zero. So how does the photon travel at sea? In other words, he's right. He's saying, look, these people are saying that the photon is massless. Okay? But that's the rest mass of the photon. They clarify that. You say, what do you mean rest mass? I mean, are we talking about how many components it has, like what it's made out of? Like 10 units of mass? Is that what the rest mass means? The rest mass of, I don't know, an elephant is 1 billion units of mass, whatever those units are, irrespective, right? We have a billion units of mass. Is that what rest mass of the elephant means? Because when we put the elephant in motion, no longer are we talking about what it's made of. Now we're talking about how much pressure or how much inertia it causes out there in some kind of interaction. We're no longer talking about how many atoms or whatever it's made of, units of mass it's made of. And again, we have that problem. Are we talking about quantity of matter of an object, or are we talking about some acceleration and the inertia or pressure or whatever it causes, or resistance, etc.? This is where the question is. Okay, what is mass? What notion do we have of mass? And fortunately, the Wikipedia says we have 7 different notions of mass. Love it. It's great. Okay, another fellow asked this question. He says, does the rope have weight? Okay. And here I can show you why it doesn't have so-called weight or mass, okay? Because it's the mediator between 2 atoms. And here's a pictorial version of that, okay? What you see there is a mountain climber, okay? And what are we saying here? We're saying that, the mountain climber essentially feels the other mountain climber that's hanging from him. He doesn't really feel the rope that's connecting both of them, okay? So we have to distinguish the mediator of light, which you see at the bottom, from the atoms. What we call mass usually is anything made out of atoms, not the rope that interconnects them. It's like we can't feel that rope, or the atoms can't feel that rope because the atom can only feel the other atom at the other end. It's like the mountain climber holding on to the other mountain climber. They don't feel the rope, even though the rope does have obviously some weight. And the question is, can we get there and take the rope away from between 2 atoms and weigh it and calculate its mass or whatever? Well, have fun with that one. Okay? So all I can tell you is it's the mediator. And as the mediator, all we're looking at is the mass at the other end, which in this case is the other atom. Then you can talk about mass, because mass is always related to atoms. It's something of this world, something in our current world, that in our macro world, that we deal with when we talk about mass. Okay, here's another issue. This guy gave me a hammer over the head. Okay, let me get this guy out here. Give me a second here. Okay, and he says, the hammer and the feather have different mass but has the same weight. I said that, okay? And he said, nobody says that, Billy. Nobody. You don't even understand the mainstream view of weight versus mass. Well, the mainstream doesn't have a definition of mass, first of all. Second, you can see this fellow. He did not say, see, you're wrong, Bill. That's not mass. You don't have the right notion. Okay, what is the correct notion? See, he didn't put the correct notion. And nobody will. Nobody will, because they know they're going to be in trouble as soon as they put something down. It's easy to tear apart whatever they put down. We don't have a definition of the word mass, and that's why, I like to always bring up Mr. Wheeler and Mr. Taylor, and they said it very clearly. They said, there's if you think that mass is quantity of matter, okay, that number does not equal mass. Okay, so this is the first lesson you got to learn. Okay, you can't keep saying that mass is the quantity of matter, because here you have high-level people, specialists, PhDs in so-called mathematical physics, and they're telling you in your face that mass is not the quantity of matter. Okay, so please get that under your belt. And if it's not the quantity of matter, what the hell is mass? That's the question for you to answer. What is mass? Why is this important? Well, because we need to figure out what mass is. I mean, there is obviously something called mass, and we use the word mass when we put it in Newton's equation. Famous Newton's equation, mass divided by distance squared. That's what we use. We use that to send rockets to the moon. We use it to calculate the gravitational constant G. And it's empirically certified. You know, we deal with this every day. Mass divided by distance squared. And so we do use the word mass, but see those two masses that we put in there, they are weight. They're not mass. We call it mass, insinuate that it's quantity of matter. But how do we calculate those two masses? Well, we calculate it by weighing them. And we say so many kilograms of mass, and that's the number we're going to put in the equation. So what we're putting there is weight. We're putting how much pressure that thing that you put there, how much pressure that object, that mass, had on the scale. That's the number you're putting. That's the kilograms you're putting in there. Kilograms is not a measure of how many atoms, how many units of mass. No, kilogram is a measure of weight. It's not, but it is. It's what we use every day. We say, weigh it, and then you'll know how much mass it has. Do you know how much mass it has? No, you know it has more mass than this and less mass than that other thing. And what do we mean by that? We mean that we have a standard, which we call the kilogram, and we measure everything against that kilogram. And they say, well, this is the kilogram. Anything that weighs more is greater than 1 kilogram. Anything that weighs less is less than 1 kilogram. What is it? Weight. We always talk about weight. And then we have this very vague definition saying quantity of matter, which these people, Wheeler and Taylor, tell you it's not mass. And it turns out that this is not the notion of mass that quantum mechanics uses, the quantity of matter. They use the same thing as the relativistic mass, the special relativistic mass, accelerate the thing, and its mass increases. Are we saying that it put more kilograms in it? Like, did the elephant eat more grass or whatever? Is that how he became bigger? He put more atoms inside his body? Is that what we mean when we accelerate the elephant at almost the speed of light and now his mass increased? No, we're talking about pressure. We're talking about acceleration. We're talking about resistance. We're talking about a lot of stuff except quantity of matter. Okay? So it's important to understand that it's this duality that comes in very handy, especially when we get to the neutrino. Okay? Keep this in mind, okay? Okay, so here's a feather and hammer experiment. It was done on the moon, for those of you who believe that we went to the moon. If you don't believe that we went to the moon because maybe you're a flat earther or whatever, no problem. At the bottom, you see it done here on Earth. Okay, the feather on the left and the little metal, you can call that the hammer, doesn't matter. They fall at the same time because they remove the air from that container. On the right, you have the actual motion with air in it. Okay, so that's the comparison. You can see what happens. Okay, so essentially, if we remove the air, okay, the feather and whatever you want, hammer, elephant, fall at the same time towards the center of the Earth. Okay. So that means that if we're in outer space, you know, and we see this, for example, let me show you. We see an elephant and a hammer. They fall at the same time because in outer space there's no air. And we're going to assume there's no air all the way to the surface of the Earth. So they would fall together at the surface of the Earth. In fact, they probably would fall together anyways because there's going to be very little resistance of air to either one of these objects. Okay, so you won't see any difference anyways. Fine. But let's do something drastic. Let's remove the Earth. Okay. Well, no. Let's take a step in between. We're going to put the elephant against the hammer, but this time we're going to put him on a seesaw, some kind of scale. And of course, the elephant's going to beat the hammer. It's going to weigh more than the hammer. And you say, hold it. In the previous case, they both fell at the same time towards the Earth. Here, the elephant seems to weigh more than the hammer. No, let me compare them again. Here's the elephant falling with. Let me put this in here. They are in free fall. There's nothing below them, and so they fall at the same time. But when we put them on the scale, the elephant beats the hammer. And you say, well, what's going on here? I mean, I thought they weighed the same out there in space, and here we can tell the difference that between the weight of the elephant and the weight of the hammer. Or you could say the mass of the elephant and the mass of the hammer. Right now we can't tell the difference. And yeah, weight is equal to the gravitational acceleration on the mass. Okay, but what are we comparing? Here we're comparing not the elephant against the Earth like we did here. See, in this case here, we're essentially comparing each one individually against the Earth. Okay, But when we put them against the scale, we were comparing them one against the other. And here the issue is, in the case of the rope model, very simple. It's how many ropes are attached from each one of these objects to the Earth. And you have more atoms on the elephant than you have from the hammer, and that's why the elephant pushes his side of the seesaw down compared to the hammer. Okay, but now again, let me remove the Earth. Okay, and now we can't tell the difference between the elephant and the hammer. Okay, in fact, we can remove the seesaw as well because it plays no role. Okay. And so this is what we would see if they're in completely outer space, out there in the middle of nowhere with no object, in the middle of two galaxies, for example, okay? Just in the middle of nowhere. Well, then you couldn't tell which one has more mass and which one has less mass or more weight and less weight, because right now you can't tell the difference. The only way you could tell the difference there is if you compare them, and you have nothing to compare them against, okay? So only under the rope model can you tell why the elephant falls faster against the seesaw, okay, than the hammer, okay, because one has more ropes attached to the Earth than the other one, right? And again, it's a question of quantity of matter, okay? So this is what I'm trying to get to, okay? It's quantity of matter. That is the definition of mass, but it gets in the way of quantum mechanics and relativity, for that matter. And in the case of quantum mechanics, it's going to be a serious problem for the tiny neutrino, okay? Because the neutrino, what are we going to talk about? We're going to say that, what is the quantity of matter of a neutrino? Are we saying that neutrino is made of all these little tiny subneutrino particles? Mereology, what is it made out of? And it turns out that neutrino is one of those elementary fundamental particles, so it's not made of anything, according to, the wizards of quantum mechanics. So it's not made of anything. If it's not made of anything, what do you mean the mass of the neutrino? Well, again, it's one of those things when you have to accelerate it. And when you accelerate it, suddenly you're talking about mass. But are you talking about mass, or are you talking about energy, using Einstein's equation, where you say, well, how much energy do you need to get that thing accelerated? Or how much energy is in the process of getting this neutrino to move? And now you take that energy equal to mc squared, and you say, well, it's equal to mass times velocity of light squared. And now you can calculate the mass, because you can say, okay, mass is equal to energy divided by velocity of light squared. Very simple, equation. And that's what they do. So they calculate the mass, not based on how many atoms or how many units of mass it's made out of, the rest mass. No, they calculate it based on dividing how much energy they sensed or detected in the system, whether it received energy or expelled energy, whichever, right? They look at that energy, they measure that, and they say, okay, let's convert it into mass through E equals mc squared. Actually, mass equals energy divided by c squared. So they're going to calculate the mass based on energy, because energy is something they say they can control. They say, oh, we know how much energy it took to accelerate a proton or a neutron or whatever. Okay, so that's something they have in their machines. I know, because I worked with accelerators. They were called implanters. I didn't work at the giga or mega. I worked at the kilo electron volt. Okay, I was a little more modest, but that's what it is. You're accelerating something, and then so you say, well, I know how much energy I needed to accelerate that. And then you take that and you want to calculate the mass of what you accelerated, and you just divide energy, kilo electron volts in my case, divided by the velocity of light squared. That's how it's done. Okay, that's in semiconductor processing. Okay, so what's the deal here? Well, we have to get to, why did we need this neutrino? Where did that come from? I mean, wasn't it simple just to say the atom is equal to the neutron, assuming, greater than hydrogen, deuterium and upwards, right? Neutron, proton, and electron. We're done. It's simple universe. Don't mess with it, right? They couldn't do that because they found out that there were some elements, okay, that spontaneously decayed, morphed, transmuted, whatever you want to call it. They changed into another element, okay? So you take a famous case is carbon-14. Given 5,000 years or so, it morphs into sodium, okay? And sodium, magnesium. No, I'm sorry, into nitrogen. What am I saying? Carbon turns into nitrogen. Carbon-14 into nitrogen-14. And that's how they calculate, the the age of bones. Like if you take a Neanderthal bone, it can only go so far, maybe 50,000, 60,000 years into the past. And you can see how much carbon has transmuted, converted, morphed into nitrogen, 14. And that gives you a measure of how much time has passed from the time that bone began to, lose its it decayed. We'll call it a beta decayed. Okay, how much time since it for the process of beta decay to take place? Okay, because they've got that down pat. They know exactly how much time it takes for carbon to morph into nitrogen. Okay, so here we have a beta decay, typical reaction using a Feynman diagram. Okay, and what are we talking about here? Let me get this here. You have a neutron. What is a neutron? Well, a neutron has an up quark and two down quarks, okay? And bear with me for a second. I'll go over that in a second, but just bear with me for now. We have these three quarks, okay? Three quarks for Master Mark, okay? That's where they got this. You say, well, is it that they discovered the quarks out there? No, it was an accounting procedure. And that's what I'm going to go over in a second. But just look at the reaction here of what happens here so that you understand the process, where they got the neutrino, okay? And so you have the neutron, which is a different animal than neutrino. Okay, neutron is a sort of like a big ball inside the nucleus. Neutrino is something else, tinier particle apparently that flies off during a reaction. So the neutron is going to turn into a proton, which is what happens like in the case of carbon 14s and all these. And some of them are negative beta decays, others are positive, so that's a little more complex. Let's just go with a simple case. Here we have a neutron is going to convert into a proton, and in order to do that, one of the down quarks, it's got one up quark, two down quarks, one of those down quarks is going to turn into an up quark. So we go from one up, two down, to two ups, one down. Okay, that's what's going to happen in this conversion, this transmutation in this morphing, metamorphosis. Okay, but there's a reaction that happens right before that, and that's that you have the weak boson. A weak negative boson, okay, comes out of there, and from there that one suffers a separate reaction, which is a separation of an electron and what they're going to call an anti-neutrino, okay. And the reason they needed that neutrino is that they had an accounting problem. They had some energy in there that they couldn't account for, and so they said, well, what is that? And they had different ideas, and finally the one that triumphed was the fact that, or the notion that there was an extra particle in there. Okay, so they have this extra particle, and they say, okay, we'll call it the neutrino, and now we can explain, what's happening here. And here's the let me show you the reaction, how it works for beta decay. And again, this is just a beta minus decay. Okay, just so you get an, well, we have both there really. You have the up quark. First, we look at charge. We're going to look at charge and we're going to look at mass. First, let's look at charge. That had to be an accounting procedure that matched out because you have to have this conservation of energy issue, second law of thermodynamics. And that was well grounded. You could not escape that. You cannot say, well, I'm going to violate the law of the law of conservation of energy, the second law of thermodynamics. No, you can't, because everybody believed in that. And they said, well, I can't. I got to stay within those bounds. And the way they stayed is, okay, let's look at charge. Charge says the up quark has 2/3 charge. And you say, is that what really it has in there? No, this is an accounting procedure. They had to create the quarks out of nowhere because they had to explain this. What they had to explain is how a proton and a neutron are made of quarks, but one has charge and the other one doesn't. And so they say, okay, this is simple. The proton has 2/3 charge, 2/3 charge, that's 4/3 charge, that's over 1, right? Then you subtract a 1/3 electron charge, the one from the electron, and then you get 3/3, which is 1. And that gives you the same charge as the electron. Okay, one electron has charge 1, and so does the proton. Okay, how do you do it for the neutron? Well, the neutron is in reverse, more or less. Remember, you have the down quarks, okay? And so you have 2/3 from the up quark, one up quark, and 2 negative 1/3, which is the down quark. You have 2/3 minus 2/3, you get 0. And so now the accounting process for neutrons and protons based on the notion of quarks matched. They said, hey, we got a solution to why neutrons have no charge and protons have charge. It's based on this down and up quark. In the case of the proton, it's 2 ups, 1 down, and that gives you 1 charge, which is the charge of the electron, and positive charge of the proton. And in the case of the neutron, you have You had to explain why it ended up with 0, and you have, yeah, it's got 1 up, 2/3, minus 2 1/3, which is the down quark. It has 2 down quarks, you get 0. So the charge was matched. They say, okay, we're done with that one. How about mass? Well, mass was a problem because you could just have neutrons, protons, and electrons. There was some other factor in there that they couldn't account for. And so that's when they created the neutrino. They say, oh, the neutrino. They created a new particle. Did they see the particle? Did they touch the particle? No. It was an accounting procedure. They needed to put a particle in there, just like dark matter, no different. They can't explain what's going on out there. They say, well, there's got to be another mass that's pulling on the stars on the outside of a galaxy. We can't see it. Okay, we'll call it dark matter. I call it dark kilograms because they just put them in by hand. They said, let's put more kilograms out there. We sprinkle it on the outside of a galaxy, and that simulates, with our computers, right, what we observe. And that's how dark matter came into being. This is no different, absolutely no different. They said, look, how do we explain proton and neutron charge? Well, we explain it with these quarks. We're just going to invent the quarks. We're going to give these guys 2/3, this guy minus 1/3. What did they do with mass? They said, well, what do we do with mass now? There's an extra mass and an extra energy in there we can't account for. And so they said, we're going to invent the anti-neutrino and a neutrino. So they created this neutrino. Okay, so now they could explain beta minus and beta plus decays. Okay, that's what they did. They simply created these particles out of nowhere. Not because Mother Nature has them out there, but it's because it's an accounting procedure. We need to get the numbers right, and we need to get the conservation of energy right. Okay, keep this in mind. This is where this is how this developed. Okay. So let's continue here. This is when all these people began searching for this neutrino. Says, well, does the neutrino exist, or is it just a fiction of mathematics? I mean, are these people just creating stuff to make the accounting go right? So guess what? They had to find a neutrino, or else they would have had serious, insurmountable problems in quantum mechanics. Okay. And so they started giving out Nobel Prizes, handing them out. In 1956, Cowan and Rines, I think it's his name, detected anti-neutrinos for the first time. And they didn't get their Nobel until, until 1995. They had to wait almost 40 years, one of them, because the other guy died in the meantime. Cowan died before that, so he didn't get the Nobel. I guess he's got it on his tombstone. Should have received a Nobel or something. 1988, first Nobel given to the neutrino guys for what? For the neutrino beam method and the demonstration of the doublet structure of the leptons through the discovery of the muon neutrino. Okay, and they kept giving more prizes. In 2002, they remember the neutrino guys again. They said, look, for pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos. So now we saw cosmic neutrinos, saw them out there in the sun, you know. And just 5 years ago, they gave it for the discovery of neutrino oscillations, which shows the neutrinos have mass. They had to show that the neutrinos have mass, because otherwise, if you don't have a mass there, then what's the point of the neutrino? And they had a problem detecting the neutrino because the way they put it is that they said it interacts weakly with matter. Whatever that means. Means that, I mean, does it interact or doesn't it? And so the neutrino, neutral means it's got no charge, zero charge. Okay, that solved that problem. But then, does it have zero mass? And if it has zero mass, then what's the point of the neutrino? I mean, you have this energy in there. It doesn't match. You need more energy. The neutrino kind of comes in there with the extra energy that you need, but energy is equal to mass. So you better find the mass of the neutrino. So they had to figure out how to create mass for the neutrino at all costs. It had to be. It must be. Otherwise, you know, we have a big problem because we cannot explain something as simple as beta decay or transmutation of proton into neutron, neutron into proton. That was the issue. So the key little thing was there that was this neutrino, the piccolino neutron. Okay. And guess what? Yeah, they finally detected it. And here's the one in 1970. They finally were able to see it, detect it, whatever, in a hydrogen bubble chamber. Okay, and you can see it's one of those. You can read it there. That line there, they think those are traces. All those squiggly lines that you see there, or any line that you see in there, they think are traces of particles. So they go in there and they say, okay, this one's Johnny, this one's Tommy, and this one's the neutrino. That's how they do it. Okay. And the question is whether, you know, can you take a photograph of motion? because if that's a trace, quite a long trace, you got some amount of time there. Is this just a simulation, a computer simulation? Is that how they come up with these? They think this is what's happening in there? Because the particles supposedly go through hydrogen. You got hydrogen gas in there. And supposedly the particle whizzes through the gas, pushing all the gas molecules sideways as it goes through. And that's what they think those traces are. They think they are the itinerary of some particle that just plowed through the hydrogen atoms, the hydrogen molecules, essentially. Okay? And so that's the first issue. Can you take a picture of motion? Or are these contrails? Is that what these pictures are? That's what they think they are. Okay. But here's the punchline for today. And this is the one you should be able to answer on the test. Okay, this is important, so pay attention, okay? Turns out that you say, well, okay, so neutrino is in there. It's part of the atom, as I showed at the beginning of the lecture. No. There's another process going on that you should be very much aware of, okay? And it's called the hocus pocus process, okay? That's why it's called quantum magic. Here's your magic, okay? And this comes from authoritative sources, Fermilab, SLAC, Stanford Linear Accelerator, okay? They publish a magazine called Symmetry. They publish their stuff there. It says, the collisions that create both pairs of top quarks, okay, and single tops, okay, borrow energy from where? Virtual particles. They get it from the virtual particle. Okay, what is this virtual particle? I never heard of that one. Okay, what is that? Virtual particles wink in and out of existence for only brief moments, but they affect interaction between particles around them. They come into existence for a moment. I guess to make the equation come out right, I guess, conservation of energy, I don't know. Okay, let's find out. The more massive a particle, the more infrequently it appears as a virtual particle. Okay, and interaction needs a very large virtual particle to create a heavy top quark. Okay, remember the top quark weighs more than the neutron that contains it, which weighs more than the gold atom that contains both of them. So you figure that one out. Physicists cannot predict the emergence of a virtual particle by the energy of the machine. So you have this machine, you have this accelerator, okay? And that's not what's going to tell you anything about where this energy came from, because it's energy outside the system. There's a reaction, and they say, well, where did the energy come from? Oh, we know. It came from the vacuum. I thought vacuum was nothing. No, you're wrong, Bill. Vacuum is a bunch of particles. Which one do you want? Which field do you want? We have the muon field, the pion field, we have the electric field, the magnetic field. We have all these fields. We even have the gravitational field in there, the Higgs field. There are all these fields there. And whenever there's a reaction here, they borrow one of these vibrating fields from the vacuum momentarily, split second. You're talking about microns of a second, very small portions of a second, borrows that energy to do the reaction, to fool us, to fool all the particle mathematicians. And then it goes back to being part of space again, vacuum, this seizing energy that's all around us. So we got a little problem here, because the way they've created this energy needed for the accounting of their equation, to say proton is equal to neutron minus electron and anti-neutrino. The way they do that, they borrow this anti-neutrino. They borrow it not from the atom. It wasn't in the atom. It wasn't in the neutron. It wasn't in the proton or the electron for that matter. No, it's borrowed from virtual particles. Virtual particles meaning particles that come in from the void, because the void is made of particles. So they borrow that energy, that particle, whatever, from the vacuum, and then they give it back. And that's how they solve the equation. See how easy it was? So all of this is magic. We don't have a procedure. We don't have an explanation for how that happens, what the mechanism is. They cannot tell you why, what caused the neutrino to pop in from the void and then go back. They don't have an explanation for any of that. And so it's magic. Essentially, they're saying, there's this reaction. There's so much energy we cannot account for. We'll call that energy in neutrino. What is energy? Energy is mass. That's the particle part of their explanation. Then they turn it back into energy, which is what they borrowed from the vacuum, this seething energy that's out there in the background. That's just magic. That's not answering the question. That's like saying, what came before the Big Bang? They say, oh, we don't know what came before the Big Bang. Why do you dare ask that question? What do you mean? You're saying that all the galaxies are flying apart. You take the movie backwards, all the galaxies are closer and closer together. You take it all the way to 14 billion years ago, and you end up with a singularity. Well, obviously, why don't you keep going with your rewinding of the tape? Go to square one, to frame number one. What happened to frame number one? They said, well, we don't know. That's an unscientific question because we have no way of proving it. We have no way of running an experiment to find out how matter came into being from nothing. Because space is made of something anyway. So I don't know, how did the something come into being from nothing? And they say it's an unscientific question because they can't prove it through an experiment. And this is no different. This is saying, we don't know where the neutrino came from. It came from the vacuum. It's a virtual particle. It comes in when we need it. When the magic wand, I need that neutrino. So they bring you the neutrino and you say, okay, now I fixed the problem. Where did the neutrino come from? Well, it came from the vacuum. And you're saying the vacuum is made out of particles? What surrounds each particle? What gives shape to each particle? What is that stuff called? More neutrinos? Is it the Higgs field that's giving shape to the neutrino field? Are they all meshed in there? Are they all superimposed? Don't they tangle? So yeah, they don't have an explanation for any of this. And that's the bottom line. Now, as a corollary, here you have one particle that does belong inside the neutron and inside the proton because it keeps the quarks together. And it's known as the gluon. And as you can see on the upper right there, gluon, the little G, I've circled it and put a little arrow there. You can see it's got zero mass and it's got also zero charge. Okay, they had to make the gluon chargeless and massless. And the gluon is that bed spring you see on the upper right there that's keeping the three quarks together, the two ups and one down, which means it's a proton. Okay, and the bed springs there, those are the gluons. But it turns out that the gluon has no mass, but when two quarks separate, they stretch the gluon, and the gluon turns into a quark, which does have mass. Okay, so when you separate these gluons, somehow the gluon acquires mass. Okay, so it's a massless particle which turns into mass, I guess, by its interaction with the Higgs field. You figure it out. Okay, so that's the starting point for our neutrino. I'm going to continue on Wednesday with our piccolino neutron. And yeah, it's something that makes you kind of think whether quantum mechanics is on the right track. And there's another corollary here, and that's that string theorists, they don't pay attention to quantum mechanics anymore. All they want to do is solve the graviton, which is what would unite quantum mechanics with relativity. So they play around with the graviton, how it falls into the black hole, and they look at what happens at the edge of the black hole and all that kind of stuff. And they don't care about all this other stuff. They don't care about neutrinos. They don't care about electrons. That's where the particle physicists over there at SLAC and LHC and Fermilab and all these other places, Brookhaven. So they play around with all that stuff. We don't care about that because these people are into vibration of lines, and they call those gravitons, and those gravitons fall into black holes. So they're in a different world. And part of the reason is that quantum mechanics is at the dead end. I wouldn't say it's a crisis because it's not an issue of crisis. It's an issue of we've already got all the equations, all of them. Or like Niels Bohr said in 1936, quantum is a complete theory. And he was wrong because they came right after that with all this other stuff. But now it's a complete theory more or less in the sense that what else are you going to look for? They were trying to answer the issue of the beta decays. Now they've answered it with the neutrino. They've got a solution for all that. They've got the equations there. What else is there? And so they keep measuring at the LHC and so on. They keep measuring to try to get more accurate values, which I'm not sure what that's going to give us. It's not going to give us a different theory, okay, different explanation. That's one issue. The other issue is that they've invented dark matter, and what all these people are into now is dark matter. They say, okay, forget about the neutrino and all that. That's over and done with. Now we're going to work on dark matter. Now we got a new cottage industry. We're going to call it the dark matter cottage industry. We got to look for that particle of mass that makes the galaxies rotate the way they do. And so these guys are working on dark matter essentially. Okay, I think maybe that was the last. 2015 was the last prize they gave out in neutrino medals. Maybe there's going to be another one down the line. I doubt it because they've got everything they need on the neutrino. Now they're going to work on dark matter. Now it's going to be the dark matter Nobel Prize. Okay, that's where all the attention is going into, the new generations. And these other guys have abandoned that completely, and they're working on string theory, on gravitons falling into black holes. And so that's the world out there. That's what all these mathematicians are working on. That's what you are paying for.